Okay, so two mean you have two graph
Okay.
like that, and one is represent a location. Like, okay, you have one column and then you have two. Yeah, location actually. One here means location one, location two. So you can see here in computer when we compute based on sample data. Okay. So actually you can see the curve here because we tell the computer to connect from one point to another, right? So actually when it compute only point by, oops, let me close it and run again. Yes, like this. So in digital control, when microcontroller compute based on the sample data from the error, and then it get the signal just sample like this and send it to digital to analog converter. You got everything correct? Oh, you have to save it. Can you save it into main directory? You save the file?
Oh, it wasn't good.
Yeah, no. You click on this one and explore to the file that you save. Where you save it? Yeah, let's no, I think it's still wrong. Because you do this one. Why this one is still wrong?
Yeah,
You can save it first and go back. Go back this one. Oh, it is actually.
Yes. Well, I will create a new one.
Is that?
Yes, maybe. Yes.
Okay. Okay, but anyway, you can plot it already. Just you just miss subplot, right? So you can do it later. I'll continue the lecture because. Okay, so the next point is about digital to analog converter by PWM method. So in some application, the part of analog to digital to analog converter involves PWM method. It means in order to generate the output to a certain level, you only control the duty cycle on pulse. So this is called pulse. So the term P here means pulse. Pulse means you have a signal that fully turn on and fully turn off like this. And width modulation means you can use analog to digital converter to set the duty cycle here. This is width, okay? Term width. DT width, like this. So let me explain application on control of motor. Suppose you have a motor and the motor can be turned clockwise or counterclockwise depending on the polarity of voltage that we supply to a motor. So here VCC is plus. So I think you can finish later, it's easy, right? So here is let's say you have a battery, this is a plus polarity, and this is ground or minus, and you have a device so-called electronic switch like transistor. So this is electronic switch, you have 4 of them. Let's say if you control to turn on this one and then you turn on this one and you turn off this, so this turn off, this turn off, so the flow like this, the current flow like this, okay, right, from here. So it means you have from this polarity from plus to minus. So suppose motor turn clockwise, okay, then if you control the switch a different way, let's say now you turn on this one and you turn on this one, but you turn off this one and you turn off this one. So the current flow like this way, here from to here to here to here to here to here, okay, still from plus to minus, right? But for the motor you can see that the current flow this way from minus polarity to plus polarity, okay. So in this case the motor turn counterclockwise. Okay. So here if you just switch on and switch off fully, then the motor is going to move at the full speed, okay, clockwise full speed and counterclockwise full speed. What if you want to control motor at a certain speed which is lower than the full speed, okay? Sometimes you need it slow, but sometimes you need it faster like robot. Sometimes you need it slowly, sometimes you need it fast. You have different wheels, some wheels need to be very fast, some wheels need to be slow, for example. So it means you have a full control. It means you need to control at the wide range of level of voltage, right? Okay, but you have electronic switch that can only fully turn on or fully turn off. So how can you do to get a wide range of voltage to the motor? That's PWM take place. So you take a certain period, let's call it TS. If you fully turn on only half and then you fully turn off half of the time, it means the average is just half the voltage. Okay, and because DC motor is first order differential equation, it has property of low pass filter. So actually the speed sorry, this one should be the speed. If let's say we apply to the motor, what is the speed? Do you think the speed would be fully turn or fully spinning and fully stop? Do you think so? No, right? Because it has inertia, right? Inertia, and so that inertia has a property of low pass filter. So actually it's gonna spin like, let me draw just at the steady state, just like this, like this, like this, like this. But if the period is very, very small, you take a very high frequency, maybe you don't see the drop, you don't see this drop, okay? You don't see the change, you see that only the constant speed. That is PWM technology. But anyway, in order to quantify the duty cycle, the width, it depends on the number of bits. Let's say you I don't know, Uno use 8 bits, 8 bits DAC, analog to digital converter. So in the full period, it can quantify up to like 255, right? From 0 to 255. That is equivalent to 2 to the h minus 1, right? So in some sense, you can only quantify the resolution with like 1 over 256. Okay, the resolution of the width that you modulate on the duty cycle like this. So actually in the next lecture, but actually in the part of multivariable, but I include the application of first order and second order as a low pass filter. You will see the simulation and you will practice the simulation of this kind of problems, okay? This kind of application. So today I only explain the concept. And do you have any question up to this? Okay, so next, let's talk about effect of sampling. So what can be problems or challenges occur when we implement sampling or digital control?
But we don't get the representative signal of the true signal, like
Right.
for the plane in the radar.
That's right, because the sampling is a kind of approximation, right? Actually, there are two things to consider. First, the numerical method applying on the discretized system itself is just approximation to solve differential equation, right? So there are many ways to solve differential equations. If you model as continuous in MATLAB or in Scilab, it will pick the numerical method that compute very accurate, that can be that can represent continuous solution, right? But if you discretize, for example, you use Euler method, okay, it means you are solving differential equation using approximation method, okay, like Euler approximation. So the sampling, okay, one thing that to consider first is about sampling. When you measure, okay, your sensor measure, for example, the speed using encoder, let's say. So it depends on the pulse per revolution of the encoder, right? It represents the resolution. So you can measure it by sampling, and this is termed as analog to digital. Okay, and okay, this one is for controller to compute based on control law or formulation. But anyway, just for simulation, let's consider only simulation now. That when you discretize the continuous system, okay, you get a different way of solving a differential equation that makes some error from the continuous one, okay. And when you sample and then you controller compute and then controller update to digital analog converter, as you can see here, every sample time, okay, 1, 2, 3 represent value k. So in here, from 0 to 1 here, the period is like sample time ts. So let's say uk you compute at this value, and then you compute at this value. So, but you don't know that the curve from here to here, you don't know how to hold it, right? Then you can only hold this value until get the new value update up to here, and then hold this value until you get a new value up to here, something like that. So in some sense, if you average, you average the stair-like curve, you got like this one, like the dash curve. So you can see that there is a delay from the original one. See, there is a delay, right? So it's not. So the larger the sample time you choose, the less accurate it can represent, right? Less accurate. I mean the sample data lessly represent. Cannot represent accurately. So two problems right now, right? The method to compute the system itself and the effects of delay from the inputs, okay, into the control system problem. So you can see the simulation here. The first one is continuous control. You have planned as continuous model, controller also continuous model, and you implement numerical method that can solve continuous system. So you get this curve, the solid line, right? And then just see the effect of this delay. So you still use continuous model, okay? You still use continuous model, but the input you inject this one, the stair-like one, right? Then you can see that this is the result, the dot curve, right? This one only affect on the delay of input. See, this one. You see the delay? See, delay something like that. And if you implement the digital controller and using Euler, it means you approximate the continuous system. You also apply this kind of zero order hole. Yeah, you will hear it more often. or the delay of the input, then you get this curve, this one, see? So actually this curve tends to go up higher. This one is accurate. In the worst case scenario, if you choose too large sampling time, it becomes numerically unstable. The system is stable. The equation of continuous also stable one, but the way that you compute it become unstable. It means you have too much error. Okay, for the worst case scenario. So you need to be very careful when you choose sampling time. Actually, the smaller the better, but you have a trade-off with the speed of microcontroller. You need so small sampling time. It means you need microcontroller to compute it very fast in order to update on time, update value to digital analog converter on time. So there is trade-off. Then it is very tricky. It depends on your experience. Okay. So you have any question? I think we still have a lot of time. Well, we still have some time, so I guess it's better to simulate the system, but simulate continuous, okay, using ITC-DCLab. So I'm gonna show you quickly. Okay, just try to simulate this one. This one it's close, right? Okay, so you need to get continuous time and you need to get transfer function, this one, continuous linear. Okay, you need two of them, one for lead controller and the one is for plan, and you need the sum. So many sum. Oh, this one is product. Sum, maybe just this one. I like the round one. Maybe this one. No, this one. Sum, which one? Just this one. And so I need the step source, step function, and then scope, okay. So for this one we need 1 over s plus 1. And this one 70. Oh, denominator. Ice. Oh, S plus 2. This one needs a clock signal. We need feedback, right? This one, right click, link style optimal. Oh, like that. Okay. Okay, and then I think I can run it ourselves first. The range should be 0 to 1. Okay, so we'll click here. Y mean just -1 to 1.5. Refresh period. And time, simulation time, simulation setup. Final integration time, this is 30 seconds, maybe we just need like 10 seconds, or maybe just 1 second. Okay, oops, oh I see, this one just 1 second. Step here, step time is 0. Okay, like this, from 0. Oops. Just 0. Okay, like this. But it start from here, not start from 0. Huh? Okay. So have you used it before? No?
I've used MATLAB 2 times.
MATLAB. Simulink?
Yes, but only 2 times.
Okay.
I'm not an expert.
I see.